In this collection of videos, we are going to continue our study of limits by introducing a new technique for computing limits, which is called L'Hopital's rule. Before we get to L'Hopital's rule, however, there are a handful of things that we need to think about. In particular, we have to get really good at thinking about limits that involve zeros or limits that involve infinity. If we solidify that mindset first, it's going to be a lot easier to talk about L'Hopital's rule. So as a warm-up, I have something that I would normally do in an in-person class as a think, pair, share. It's a little hard to do when you're watching videos on your own, so let's do it this way. You do the thinking part. In terms of the pairing, imagine that you're paired with Jerry from Cheer. And so when you share with Jerry, Jerry's going to be real excited for you and say, "Yes, you did it. You did awesome. Amazing. Love your work." So pause, take a minute, and see if you can come up with the answers for these three limits, and resume the video when you're ready. In short, the answers for 1, 2, and 3 is that this limit does not exist, this limit is infinity, and this limit is 0. Now, you may have those answers and feel really great about it. What I'm going to do is show you a couple of different methods that you could use to start understanding the concepts of why these answers what they are in Mathematica, so we get some more practice with Mathematica. So here's my Mathematica document. I've already done a warm-up. The first example that we were looking at was the example of 42 over x as x was approaching 0. Now we can approach 0 from two different directions. So what I'm going to do is just make a little table of values of the function 42 over x as x is approaching 0 from the left and as x is approaching 0 from the right. So remember, I'm going to be using Mathematica's table command. If you ever want to know more about a command in Mathematica, you type it in with a question mark ahead of time and it gives you some syntax information. The first thing I put in my table is the thing I want to look at, 42 divided by x. And then I follow that expression with a comma. I then use braces to tell Mathematica the variable that I'm using, the starting x value I want, and the stopping x value I want. Now I'm computing a limit here, and so I don't actually want to divide by 0. Mathematica will give me an error if I try to divide by 0. Let's imagine approaching from the left, and let's think about starting maybe at -1. That's kind of close to 0. And let's think about stopping when I reach -0.1, which is pretty close to 0 also. And by default, Mathematica will step in increments of 1 in between Imin and Imax. So if you want it to step with different increments, you can give another parameter saying what the step size is. So let's use tenths as how we want to progress. So this table will give us values of 42 over x, starting with x is equal to -1, stopping with x is equal to -0.1, and it will hit -0.9, -0.8, -0.7, all the way in between. So here's the value of 42 over x when x is -1. This is -0.9, -0.8, all the way down to -0.1. So you can see that we start at 42 and stop at 420 with negative signs in front of everything. Let's get even closer. Let's go to -0.01. That's even closer to 0. And let's take steps of size 1/100th instead of 1/10th and see what happens to our table. Well, it gets much longer, but it starts as it did before at -42. But now we've gotten much closer to 0, and our number, instead of 420 as it was before, is 4,200. If I were to get even closer to 0 by adding these values here, well, my list is going to get really long. That might be hard to read. So maybe if I want to get that much closer to 0, I want to start at something like -0.01. And as I step much closer to 0, now I have 42,000 here. So if we believe in the power of patterns, we believe that this function is getting really huge and all of the values are negative because I'm approaching 0 from the left. Now you can either experiment around with the table function, trying to go from 1 to 0.1 in steps of size 0.1. If I try to make this table, there's a bit of a problem. Notice that it doesn't work. That's because it wants to start here and stop here, and 0.1 is less than 1, so it doesn't understand that I should be walking in reverse. I can fix that by taking steps of size negative 0.1, so I indicate that I want to walk in that other direction. And notice that the things I'm seeing happening here are exactly the same as what I was seeing when I ran these tables for 42 over x with the negative x values, except that all I'm missing are minus signs. I'm getting all the same numbers, just no minus signs. That leads me to believe that as I approach 0 from the right on 42 over x, that I'm getting the same values as I did before, but I don't have any minus signs. So as I approach 0 from the left, my limit is negative infinity. As I approach 0 from the right, the limit of this function is positive infinity. Those two values are not the same, so this limit does not exist. If you want to verify that graphically, we could ask Mathematica to plot 42 over x as x goes from -1 to 1, and Mathematica will give us a picture to show that that's indeed what's happening. The values in this direction are becoming very, very negative. The values from this direction are becoming very, very positive. These two things are not the same, so this limit does not exist. We don't have to go back to square one and re-envision what's happening here. Let's compare that to the behavior of what ought to be happening in the second example. When I take a negative number and square it, I now get a positive number. Nothing conceptually has really changed. As I'm approaching 0, imagine that what I'm getting are a bunch of fractions right here. Small numbers, 1/10th, 1/100th, 1/1000th. Now I'm squaring them. That has the effect of making 1/10th into 1/100th, 1/100th into 1/10,000, etc. So it makes this 1 over an even larger number. And when I have a fraction in this denominator, 1 over 100, I need to reciprocate that to turn it into a multiplication, and that's where I'm getting numbers like that 4,200. So it makes sense that if I'm dividing by a very small number here, that overall the whole fraction should be evaluating to a very large number, maybe with a minus sign, depending on how I'm approaching 0. But the instant I come in and I square the denominator, I get rid of that minus sign, and I end up with just a very large number. That resolves this issue of one of these directions having a negative infinity and one of these directions having a positive infinity. In fact, if I come over here and just change that x to an x squared, my image now shows from both directions approaching a positive infinity, and that's how our second example has an answer of infinity, while our first example has an answer of the limit does not exist. The last example here is probably the easiest. As x gets really, really big, as x starts 1, 2, 3, whatever, these numbers are all smaller than 42. I'm getting some larger numbers, but eventually x is going to be a number like 42 even. And 42 divided by 42 squared, that'll give me a 1 over 42. That's really small. And as x gets bigger and bigger and bigger, 42 has nothing on the denominator. I'm taking 42 things and dividing them into so many pieces. The size of each piece is really small. And so this limit is going to be 0. And again, you could investigate that graphically. Instead of starting here at -1, maybe start at 100 and go out to 400, graphing the same thing, and you can watch as that approaches 0.